Hi, welcome to this course on computational thermodynamics and kinetics of materials. Let's continue with more physical metallurgy ideas. In this class, we will see about extended and emergent phases and how to see tie-line and tie-triangle in a ternary diagram. And more importantly, vertical sections. We'll see about pseudo-binary and quasi-binary sections. What are extended and emergent phases? Unary systems, if you consider, for example, pure iron, temperature versus pressure diagram, we have seen this in one of the previous classes. What happens at atmospheric pressure when temperature changes? We see BCC phase, FCC phase, again BCC phase and liquid phase, right? So these phases are called unary phases, and in the x-axis we don't have composition here, it's pressure. Okay, so atmospheric pressure, we have BCC, FCC and liquid. These are the unary phases that we see. So from this, let's start and understand what are extended phases. Extended phases from lower to higher order. You see, this is a binary diagram here, a two component diagram, FECR is drawn. So we now go from lower, meaning unary, to higher binary order. So we'll see what are the extended phases here. Since it is pure iron here and this diagram is at atmospheric pressure, you can see with 0% chromium, pure iron, BCC phase, FCC phase, again BCC and liquid. Okay, this BCC is labeled here and this is also labeled here. Okay, so this region and this region is BCC. What does it mean? It means as chromium is added to iron, this entire region is a single BCC. Okay, similarly, this region is FCC. What does it mean? It means these are phases which are extending from unary side, right? From this side, BCC is extending, from this side, FCC is extending. Okay, these are extended phases, phases extending from lower order to higher order. In this case, unary phases extending into binary composition space. In iron chromium system, these are FCC and BCC, which are solid solutions, and liquid also at high temperature. This is also extending into binary space, so that is also an extended phase. Alright, so you can imagine this chromium here, this is BCC from room temperature till melting point. So this BCC, as iron is added, can be imagined to extend into the binary regime, right? So that is another way to look at the BCC, but in any case it is an extended phase. Now, what are emergent phases? Think about the sigma here in iron chromium system. So what are emergent higher order phases? In this case, iron chromium system, it's sigma phase. It's a emergent binary phase. Why do we call it so? Because it does not extend from a unary system, right? From this iron side or chromium side, it is not extending. And what only appears in the binary composition space. Only when iron and chromium are mixed in this composition range at this temperature, it's going to come. And sigma phase has tetragonal crystal structure. Tetragonal crystal structure is not there for iron or chromium at any temperature. Okay, so totally new crystal structure. No unary phase has this tetragonal crystal structure. That's the reason why we call it a binary emergent phase. Now look at this AlNi system. And in this based on the sources of phases, whether it comes from unary or not, can we tell which are the binary, which are the extended phases and which are emergent phases? So which phases are extending from unary to binary? Aluminum solid solution, nickel solid solution. Okay, this phase and this phase in bracket, when we put in ASM diagrams, it is used for solid solutions, right? So nickel solid solution, we can clearly see this pure nickel is some FCC, let's say, and it is extending into this region, accepting the aluminum into that, right? So this is a extended phase. Similarly, in the left extreme, there is pure aluminum, and barely there is any solubility for nickel in that. If at all we zoom into this region, we may see a small solubility, that's all. Okay, so that is about aluminum solid solution. So these are solid solution, therefore they are extending from unary to binary. What about the emergent binary phases? All the other phases, Al3Na, Al3Na2, Alna, Al3Na5, Na3Al, all these compounds that are here, they are all all these intermetallic phases, they're all emergent phases. Okay, so when we say these intermetallic phases, recall that aluminum nickel can be AlNi phase. Okay, this phase, this can be imagined as two sublattices, one with only aluminum and one with only nickel, are interpenetrated. I hope you remember that. So two sublattices interpenetrated to form this AlNi phase. So this particular thing can be done for other intermetallic phases also. Okay, they can also be imagined to have such sublattices. Need not be only two sublattices. And occupancy, there is something called occupancy of sublattices. We'll talk about that later when we do the modeling part. So this understanding is important. These intermetallic phases here, they can be imagined to have sublattices interpenetrated and all, because their crystal structures are going to be complicated. Just now we saw about sigma phase, a tetragonal crystal structure. Okay, so those can be modeled better, that their they have a particular stoichiometry also. Okay, so they can be modeled better if we consider them to have the sublattices. And in phase diagram, they are considered as emergent phases, right? Fine. So you test your understanding with this example. This is an aluminum chromium system. FCC phase is there on one side, BCC phase is there on the other side. Liquid is there here, and multiple intermetallic phases are standing. Okay, so this is a slightly zoomed in version of this bottom region here. Okay, questions are this: which phases extend from unary to binary? Which are emergent binary phases? Pause, think about the answer. If you are ready, play the video and see the answers. Extended phases from unary to binary are liquid, FCC and BCC. Okay, of course, BCC's extension we can clearly see, liquid's extension we can clearly see. FCC's extension is very, very small. Emergent binary phases are all the other phases, all the intermetallic phases. Right. What about the extended phases in ternary regime? So this is an isothermal section of ABC system. Solid phase is stable here, liquid phase is stable here. Two phases are stable here. And what we see as these lines are tie lines. We'll see about them in detail after 2 slides. Now in this section, phase S, this one has crystal structure of A. That means you can say unary phase extends into a binary composition space. This A here, as C dissolves in A, it extends like this. So A's crystal structure is going to extend like this. That is the S phase. Okay. Similarly, B also dissolves in A. It is extending like this. That is also an extended phase. Unary phases extending into ternary composition space. Again, you can imagine this phase C and B can dissolve in A, right? Both are dissolving in A, forming this S phase. So we can say this entire S phase is also from unary, right? What about the emergent phase? Consider on ABC system, isothermal section. As a dot here, it's AC2 phase, meaning at particular stoichiometry of A and C, you see this emergent phase in binary side. Of course, this dot also will not be given in most of the diagrams. I am putting it for the sake of understanding. So this is a emergent binary phase. In a binary phase diagram, this may look like a line, vertical line, line compound, but this is just a dot in the ternary space, right? Now, this AC2 is an emergent binary phase, all right. If it extends into a ternary space like this, what does it mean? It means that as B is added, it can replace either A or C or both, but it will keep this stoichiometry and extend into the ternary space. Up to this much amount of B can be added. You know how to read the composition of B in this dot here. So binary phase can extend into ternary composition space, B dissolving in AC2. Or it may be that this entire solubility of B in the AC2 is not there and it is just a dot like this. Okay, so there can be no solubility for B in AC2 as well. Okay, quite possible. Different intermetallic phases behave differently. Now what about this phase here, ABC? So A, B, C are equal in this stoichiometry A1, B1, C1. You can imagine this to be near 33% for A, B and C, 33% each. Okay, so this kind of phase may appear in some system. For example, TiNiSn, titanium nickel tin system. In that you will see a phase in the exact middle of the diagram. That's called TiNiSn phase. So that phase can be considered as an emergent phase. Okay, it's an emergent ternary phase, appears only when these three elements join in this ratio. It may have an entirely different crystal structure as well. Okay, that's about the extended and emergent phases. What about ternary tie lines and tie triangles? Let's understand them. So this isothermal section is here. I told these are tie lines. Okay, you can see tie lines directly indicate this liquid and solid compositions. Okay, so if tie lines, the ends of tie line directly indicate the composition of two phases. If your overall composition, let's say, falls here, it will have two phases. What is the composition of two phases? Solid will have this composition, liquid will have this composition. Now, what about tight triangle? This is a tight triangle. This triangle here, it is touching three phases, alpha, beta, and liquid, and that it encompasses a three-phase region. So, if your overall composition falls within this, it has three phases in it. The microstructure has three phases in it. So, these three corners touch three single-phase regions here, here, and here, and by that, it indicates the composition of three phases in this region. You know how to read the composition for each point. This is the composition of alpha, this is the composition of liquid, this is the composition of beta. Okay. And phase fractions can also be calculated from this tight triangle by applying the lever rule. How do you apply lever rule in a tight triangle? Let's see that. Okay. So this is a tight triangle here, same alpha, beta, liquid from the previous slide is here. Let's see how to calculate the phase fractions. So this is a recorded animation. So you see, if you want to find out what is the fraction of beta, you click on find proportion of beta. You will see that the red line which goes through the overall composition X touches the opposite side, and you can measure the lengths on the opposite side and the total length, and then use the lever rule. Percentage of B is that length 5.5 divided by 18.4, which comes out to be 30%. Then if you want to figure out what is the percentage of liquid, then from liquid draw a line to the opposite side, measure the lengths 3.3 by 13. That is going to be the fraction of liquid. Okay. This is how you figure out fraction of phases from tight triangle. Now test your understanding with this. This is a ABC system. So this is one tight triangle alpha, beta, AC3. Which phase extend to ternary region from unary in this ABC system? Okay. That is question number 1. Which type of phase is AC3? Is it an emergent phase or extended phase at binary level? Does it extend into ternary space? That is the second question. Third question is, does B have any significant solubility of A and C? Then fourth question is with regard to this orange dot. What are the phases, their compositions and phase fractions at the overall composition indicated by the orange dot? Okay. Answers are here. For first question, it is alpha. Which phase extends into ternary region? Only alpha extends into ternary region. And B, if you see which type. And for second question, binary emergent phase. AC3 is a dot appearing here. So it's a binary emergent phase. And it does not extend into ternary region. Does not dissolve B and become a line or a range and all. Okay. So it's not a phase extending to ternary regime. And for the third question, does B have any significant solubility of A and C? Answer is no. You can see alpha has solubility for C and B extending like this. But B is not at all extending here. We are not marking anything as beta and all here. So B is only here, does not dissolve any significant amount of A or C. And for the fourth question, what are the phases in this orange dot? Alpha, B and AC3. And their compositions and phase fractions. Their composition and phase fractions we can know from tie triangle. Okay, we will we'll see that in the assignments as well. Let's understand one of the most important ideas for higher order systems, vertical sections. Okay, so think about ternary prism, and there are some colored sections given here, blue, red, and green, and all. You can see they are at different angles. So like this, different blades can be taken and the prism can be cut and the sections can be seen face on like this. You can see here in this diagram there is this section going from liquidus to solidus like this, and that is appearing here, liquidus to solidus like this. So it's starting from a binary combination, not a single element, 30% A, 70% C. This point here is coming here. Okay, so that is where the ternary vertical section starts, right? How to think about tie lines in this? Okay, are tie lines there in this diagram? Can we apply them and see the compositions, apply the lever rule and all? No, we can't do that. If you see carefully, if in the binary side, let's draw a tie line like this. So this is a tie line here. This tie line actually intersects the vertical section at a dot. That's all. Okay, the tie line does not lie in this plane, right? So tie line will actually be in this dot only. It is not a line that you can draw like this. So tie line cannot be drawn in this section. Think about it. If you take a isothermal section like this and visualize in this kind of thing, where this vertical plane will go, it will go as a line, right? It will go as a line like this. Okay. So this line, how does it relate to tie line? If I bring the isothermal section back, you can see tie lines are like this. Okay. So you can see it is just going across all the tie lines. That's all. This is how you will get the vertical section. It will not have the tie line in that. In fact, if the diagram is slightly different like this, tie lines go like this, right? And in that also, if you see this vertical section, it is only going across all the lines. It doesn't have any tie line lying in that. But if we make a vertical section like this, okay, and you can see one of the tie lines is lying in that. So only for particular vertical sections, you can have the tie line lying in them. Based on that, we can differentiate two types of sections, vertical sections. One are called pseudo-binary sections, in which tie lines do not lie. Okay, so most of the sections are going to be pseudo-binary sections. Okay, so tie lines is not going to be there in that. But some of the sections which will have the tie lines in them, they are called as quasi-binary sections. So this is one of the important understandings. With this, let us stop today's class. Thank you. I hope the lecture is quite useful. See you in the next class.